This mini lecture just touches briefly on connecting molar mass and density to gas law calculations, and summarizes all the different approaches we should now be able to use in stoichiometry problems. Examples of calculations involving both these concepts will be done in class. A simple substitution and rearrangement within the ideal gas law will allow us to determine either the density or molar mass of a gas using gas information. But before I show that derivation, let's recall the units of density. Mass divided by volume. As mentioned in the first mini lecture for this chapter, gas density is different from solid and liquid density in that the volume of a gas can change drastically depending on the temperature or pressure of the gas. Therefore, the density of a gas is highly dependent on these conditions, as well as on the mass of the gas. For example, two types of balloons that you are probably familiar with are helium balloons and hot air balloons. But why do these balloons float? Well, the density of the gas inside the balloon must be less than the density of the air around the balloon in order for it to rise and float into the atmosphere. So, in a helium balloon, the difference in density is due to the incredibly small mass of helium compared to the average mass of air. The concentration of gas molecules inside the helium balloon may be the same as the concentration of gas molecules of air outside the balloon, but since the mass of those molecules is so different, with it being much less for the helium, then the density is much smaller for the helium, even though the number of gas molecules per volume might be about the same as the air that surrounds the balloon. In a hot air balloon, the air on the inside of the balloon is the same as the air outside the balloon at first. But as heat is applied to the air inside the balloon, the gas molecules start to move faster, which makes them expand and press on the balloon walls and take up more volume. This causes the density to decrease enough that the hot air balloon starts to rise into the atmosphere. And the concentration of the air on the inside of the balloon would actually be less than the concentration of the air on the outside of the balloon. When the air inside the balloon begins to cool down to match the surrounding air temperature, the density and the concentration will then increase again, and the balloon will start to descend. The densities of liquids and solids do change a little bit with temperature, but not as much as gases. And the densities of liquids and solids are usually pretty constant with changes in pressure in most normal situations, whereas with gases, they're very sensitive to pressure. To develop an expression relating the density and molar mass to the ideal gas law, we begin with the ideal gas law and note that moles and volume are two terms that will connect to the density. Recall that the moles of a substance can be determined by dividing the mass of a substance by the molar mass, and that density is just the mass of a substance divided by its volume. So there are connections between all three of these equations that we can take advantage of. First, we can substitute the expression for moles as the mass divided by the molar mass into N in the ideal gas law. Then, if we rearrange the equation by moving the volume to the right side and the molar mass to the left side, we get this equation that has the expression mass over volume, which is equal to density, so we can replace mass over volume with density. This gives this final restructured version of the ideal gas law where molar mass and density are present instead of moles and volume. Again, this shows that the density of a gas is dependent on the temperature, pressure, and molar mass of the gas, and that we can use the density of a gas at a given temperature and pressure to determine the molar mass and therefore the identity of the gas. So be ready for problems that may ask you to identify what gas is present in a certain problem, where you would then want to solve for the molar mass to identify the gas. Finally, this is the point in the semester where I like to summarize all the different ways in which we can now approach stoichiometry calculations. Recall that the basis of stoichiometry is to use the mole ratios of chemical compounds within a reaction to calculate the moles of each substance involved in the reaction. So, since stoichiometry is all about the moles, we want to always be thinking about the different ways in which we can get to moles from various starting points. For example, we first learned how to start with atoms or the number of molecules of a chemical compound and convert to moles using Avogadro's number. So, a stoichiometry problem may begin by giving you the number of atoms or molecules of a substance in a reaction, or it could end by asking you how many atoms or molecules of a substance are produced or needed. In either case, as long as you know how to convert back and forth between the number of atoms or molecules and the number of moles using Avogadro's number, then you can solve the problem. Then we learned how to convert from mass to moles and vice versa using the molar mass of a substance. This was the most basic form of stoichiometry that we focused on in the last chapter, where the mass of a substance is given at the beginning of the problem, and the problem then asks you to solve for the mass of a reactant that's needed or the mass of a product that's produced. Then we learned how to convert from a volume of a solution to moles in the solution using molarity, or the concentration. Again, the information about solutions can be used at the beginning before using the mole ratio, so that you are taking the volume and the molarity of a solution to get the moles that are contained in that solution. Or this could be something that needs to be used at the end, after the mole ratios, where you'll have a number of moles of something in the reaction that you want to convert into a volume of solution that is needed or produced. Finally, we have now seen that we can determine the moles of a gas using the ideal gas law and the pressure, temperature, and volume of the gas. So, if the conditions of a gas are given at the beginning of a stoichiometry problem, you can use the information to determine the moles of the substance involved in the reaction to then use in a stoichiometry calculation. Or you could also be asked to give your answer as the volume or pressure of the gas produced or the gas needed in the reaction, where as long as you know the moles of gas that are needed if it's a reactant or produced if it's a product, and you know the other conditions at the end of the reaction, like the pressure or the volume or the temperature, then you can solve for any one of those values. This concludes the fourth mini lecture for material from chapter 11. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.